Welcome to The Explainer. Today, we are diving headfirst into something that is, well, it's beautiful, it's chaotic, and it's almost impossible to predict. We're talking about turbulence. And we're going to explore how engineers try to tame this wild force in the world of computational fluid dynamics.
So let's kick things off with a question that honestly feels a little bit backwards. Think about it. We can map the movement of entire galaxies, right? But we really struggle to perfectly predict the tiny swirl of air coming off a car's side view mirror. How is that possible? Well, it all comes down to one incredibly powerful, chaotic force. And that force is turbulence. It's not just some random movement. I want you to picture this. You've got these big swirls of fluid, and they're breaking down into smaller and smaller swirls, which then break down into even tinier ones. It's this cascade of energy that's happening all at once. And you see it everywhere, from our weather patterns to the inside of a jet engine. This chaos is exactly what makes simulating fluids so incredibly challenging. So how in the world do engineers even start to tackle this? Well, here's the roadmap for our journey today. First, we're going to talk about why a perfect simulation is basically impossible. Then, we'll look at a really clever shortcut that makes it all work. We'll explore the different families of models, and then finally, we'll get into the real art of picking the right tool for the job. Okay, let's just get right into it. Why can't we just point our biggest, baddest supercomputers at the problem and simulate turbulence perfectly? What's stopping us? Well, in a perfect world, we'd use a method called Direct Numerical Simulation, or DNS for short. The idea here is actually pretty simple. You calculate everything. You solve the fundamental equations of fluid motion to track every single swirl, from the biggest currents all the way down to the tiniest little eddies where energy finally dissipates. It's the gold standard. But here's the kicker. The computational cost is just staggering. It scales with something called the Reynolds number, which is just a measure of how complex the flow is, cubed. So if you double the complexity, you don't just double the cost. Nope. You increase it by 8 times. For pretty much any real-world engineering problem, like a full airplane, DNS is just completely out of reach. Not just for the computers we have now, but for any computer we can even imagine. So if the perfect simulation is off the table, engineers obviously need a different plan. They need a practical shortcut, something that gets the job done without having to wait for the next century's supercomputers. And that shortcut is called RANS. Now, instead of trying to track every single chaotic wiggle in the flow, the Reynolds-Averaged Navier-Stokes approach does something really brilliant. It just averages the flow out over time. It smooths out all that chaos. This lets us focus on the main average flow. And then, and this is the key part, it uses a separate model, an approximation, to account for the effects of all that turbulence we just averaged away. The benefit here is just massive. I mean, by not having to resolve the tiniest, fastest moving bits of turbulence, RANS slashes the computational cost. This is what makes it possible to simulate incredibly complex systems, like the airflow through an entire gas turbine engine or around a whole car, and get an answer in a time frame that's actually useful for design. Okay, but RANS isn't just one thing. It's actually a whole family of models. And to really understand them, we need to see where they fit in the bigger picture of how we simulate turbulence. This chart really shows the whole landscape of choices we have. Way up at the top, you've got that super accurate but impossibly expensive DNS. Then, kinda in the middle, you have these hybrid methods like large eddy simulation. And down at the bottom, really forming the foundation for most of the engineering that gets done every day, you have the RANS models. And this table really gets to the heart of the matter. It is always a trade-off. As you move down from DNS to RANS, the computational cost plummets, which is fantastic. But at the same time, you're also moving a little further away from the raw, perfect truth of the physics. The real skill of a great CFD engineer is knowing exactly where on this spectrum they need to be for their specific problem. All right, so since RANS models are the absolute workhorses of industry, let's zoom in a little bit and meet the family. You'll see pretty quickly that they're not all created equal. Each one has its own personality, its own strengths and weaknesses. So these models are basically grouped by how many extra equations they solve to describe the turbulence. The simpler ones use a concept called eddy viscosity, which is a fancy way of saying they treat the effect of turbulence as if it just makes the fluid a little bit stickier. The more complex models, though, they go a step further and they try to directly solve for the specific stresses and strains caused by the turbulence, giving you a much more detailed picture. So let's compare two of the most popular workhorses, On one side, you've got Spalart-Allmaras. It's really fast and stable, which is exactly why the aerospace industry loves it for things like calculating airflow over a wing. Then, on the other side, you've got the k-epsilon model. This one is a super versatile industry standard, and it's especially good for flows that are confined inside something, like air moving through an engine or water flowing through a pipe. But see, here's a limitation of a model like k-epsilon. It makes a really big assumption that the turbulence is isotropic, which just means it behaves the same in all directions. Now, for a lot of simple flows, that's totally fine. But what about really complex, swirling flows? That assumption starts to break down. And that's where a more advanced Reynolds stress model comes in. It doesn't assume isotropy, so it can actually capture that swirl accurately. But what's the catch? You guessed it. It's way more expensive computationally. So this brings us to what is maybe the most critical part of the whole process for any engineer. You've got all these options. How do you actually choose the right model? How do you pick the right tool for the job? I think the most important thing to get is this. There is no single best model. It just doesn't exist. As this quote says, there's no magic bullet. Each model is a specialized tool, and it's built on a set of assumptions. The real skill is knowing the physics of your problem so you can pick the tool that has the right assumptions.
You know, the selection process is really just a methodical balancing act. First, you have to know what you're even looking for. Is a rough estimate of drag good enough? Or do you need to know the exact point where the flow separates from a surface? Next, you got to be realistic about your computer resources. Then, you analyze the specific physics of your problem, and you pick a model that's designed to handle that. Always remembering that final, absolutely critical step. You have to validate your results against real-world data. All right, let's bring this all home. After our quick tour through this really complex world of turbulence modeling, what are the most important things you should walk away with? First, and this is huge, these models are just that. They're models. They're brilliant, incredibly useful approximations, but they are not the fundamental laws of physics. Second, every single simulation is a compromise between cost and accuracy, always. Third, your choice of model has to be driven by the physics you're actually trying to capture. And finally, and I can't say this enough, never, ever trust a simulation blindly. Validation isn't optional, it's absolutely essential. And that leaves us with a really fascinating question for the future. As our computers get exponentially more powerful, are we eventually just going to brute force every problem with perfect DNS simulations? Or is the future of engineering not really about more power, but about developing smarter, more elegant models that help us outsmart the chaos of turbulence? It's a great question, and it's one for the next generation of engineers to answer. Thanks for joining us on The Explainer.